Okay, let's go back to the class. Okay, so I'm going to talk about this one. Okay, Word2Vec. It is invented by Google in early days. Okay, if you want to take look up some reference. Okay, here's the English version. It's the traditional Chinese version, but I will draw some figures to help you to know what exactly it is. Okay, so basically, first of things, we have a very specific task, right? We have to convert sequence, okay, and it is text, to numbers, and usually it is in vectors way, right? So that is a very specific task need to do. Okay, so the first thing is that I think this in Word2Vec is invented by Google in 2013. Okay, so basically, I would like to start from autoencoder. Okay, right. Just a revisit autoencoder, just a review. Okay, autoencoder is that we have a certain input, right? We have X, and we have some hidden layers right here, right? And for autoencoder, we would like to X the neural network to help us to train a lot of weight, so that the x1 prime, the x prime, and the x, their maybe their loss function is written in this way, right? Their loss function will be very small. So the linear space used right here will try to keep all information from x1 to xm in a more compressed way. So usually we say that k is less than m, right? In this way. So basically it is not supervised learning, or not even theoretically not unsupervised learning, because the data we would like to learn is right here, is our input data, and the output data right here is exactly the same as the input. So you can call it self-learning or semi-supervised learning, whatever it is okay. But basically we don't have a specific target y, so that we don't have to label it. And right here, the autoencoder, the result, the linear space in the middle, made by the hidden layers, is exactly what we want, right? That is autoencoder that we talked about before. And however, if we would like to take, because we don't usually, okay, I say usually we don't like to do labeling, because it takes many times it's a human intensive job. So in order to do such kind of task, we try to use the concept of autoencoder. Okay, so basically it's like this. Okay, I have several words. For example, this is a fine book. Right, that is the sentence. That is the word we can find, for example, from Wikipedia. You can download all the articles in from the Wikipedia and use it as a corpus. Corpus 我们讲过 ，corpus 就是文本集嘛哈。Use as a corpus, try to do such kind of training. Okay, so firstly, you have to, for example, if it is a 5 inputs right here, okay, and usually you can still create, for example, any neural network, any different algorithm right here, which is okay. But actually, we like to output something, right? there are several different outputs. Okay, when we deal with such kind of word embedding. Okay, one of the embedding is like that. Okay, I only output one single word. Okay, but what exactly this output stands for? Okay, so if you want to know the name is a Hsiao. Okay, but I draw it right here. Okay, for example, you can firstly convert this word by using one hot encoding, or simply just give it a number. Okay, for example, this input is for example 00100. It stands for this. Okay, this stands for is. Okay, and this you can use any kind of encoding ways. Okay, to use it as an input. You can even use a PCA to compress this vector, because it is a very large vector. No matter what, you can simply just represent the original text by using a very simple encoding numbers. Okay, that is your input. Okay, when we talk about Hsiao, okay, and BOW stands for back of words. Okay, and what exactly this Hsiao does? That is, they only takes the words around it by certain specific position, and would like to ask this, no matter it's a neural network or whatever structure, like to output up, which is the word in the middle. Okay, maybe the is I simply just write the word right here. Okay, and we want to output this, and of course, it could be more generally. Okay, it could be many different outputs, and that is your vocabulary, means your dictionary. And there is a probability. Okay, you can simply just use softmax, right? Softmax layer will try to figure out what is the probability of each output, right? So maybe this is the largest probability that possibly this word should be or could be, I mean. So basically, this kind of task is more likely closed. 中文讲没有？这个有时候我们在设计这样子的这种所谓的 word embedding 的时候，这是其中一种概念，叫做 Hsiao。Hsiao 这个概念呢，其实跟克漏字是一模一样的。我们会认为说，如果你很懂一个语言的话，就像我们中学的时候考英文一样，你应该要很会做克漏字这件事情，对吧？因为克漏字这件事情就跟这边讲的，你必须要知道前后文，比如说 this is， 后面是 find book， 然后你中间就要刻那个字，克漏字嘛，克漏字就是要把那个字填上去嘛。所以实际上呢，这样子的克漏字的这个概念就可以在 word to back 里面被应用出来，对不对？所以你有大量的文本从 Wikipedia 上面来，你就把每一个句子全部都拆出来，然后呢，以这个例子来说，就是它需要5个连续的字，然后前面2个就是输入前面2个的 encoding， 那 encoding 随便做都可以 ，1 gram、1 hot 随便做都可以哈。然后后面是个后面的字也做，可是你把中间的字留下来，然后你在 training 的时候呢，你就输入嘛 ，this is find book， 然后它答案是2。那当然，你有 Wikipedia 上所有的文章嘛，就努力的 train， 你把所有连续5个的东西全部都丢进去 train。那中间的这个 neural network 呢 ，supposedly 它就会根据 this is 跟 find book 的东西，然后想办法去 train 中间的 weight。其实这跟 autoencoder 非常的像，只是 autoencoder 是输出原本的东西嘛，就是 this is a find book， 它就输出 this is a find book， 但不是 在 C 报这边呢是 list， 你给 this is find book， 要输出2这个字，啊，或者是说你前面可以用 somax， 要输出最大 probability 的这个字是2，都可以。啊，就是形式上，概念上是这样，但是形式上你 implement 有很多种。好，当然 paper 上呢就只有一种了哈，但是你自己可以规划自己的这种 convert 这种所谓的 text to number 的这种形式。所以你说它是 supervised learning 或是 unsupervised， 其实都不是，因为它跟 auto encoder 一样，它的答案就在题目里面，对吗？我们不是原本输出是 x1 到 xm， 然后输出是 xe prime 到 xm prime， 可是这是一样嘛？你那句话你就把那个答案 this is a book 的那个的中间那个当做答案，然后输进去。所以这个会造成一个状况是说，它会不断的学中间的这些 weight， 使得在 this is find book 的情况之下，输出 A 的几率是最高的。那你记得我们刚刚讲的说，我们刚刚在那个动画那个图里面不是看到吗？我们希望这个 latent space， 啊，这个 latent space， 就是这个 embedding 的结果啊，这 embedding 的结果 A 的那个答案，那个 latent space 在哪里呢？那个 latent space 呢，应该是在这里，就在这里，就是红色的这里哈，就是不管你怎么样输入东西之后，你的 neural network， 你中可能是个 neural network， 你最后总是有某一层嘛，那一层等一下要输出成 softmax 来决定说是这个字几率最高嘛。可是在它的前一层，是不是应该要包含所有的 information 关于应该要输出这个字，对吧？所以最后的 softmax 才可以轻易的输出这个字，对吧？所以呢，有的时候呢，我们就会用红色的这一层来表示，就是表示这些关系了，好，表示这些关系，好，可以吗？好，这个是一种用法，好，你也可以用这个红色这一层来表示这个字了，好，这个都可以哈。好，那基本上呢，就是不断的 train 之后，就会有这样的结果。哦，你用超大量的字，那它会有一个很妙的状况啊，就是说，我们不是希望说字的 embedding 如果原始的意思是一样的，那它在 latent space 里面的距离应该要很紧才对，很短一样。像刚刚讲的 help 啊，或是 add， 或是 assist 这三个字的，其实它的意思都是帮忙嘛，对不对？那它的 embedding 应该的数字也要差不多相近。好，那它是怎么做到的？你可以看下面这个例子哈。假设this is a fine book 啊，假设我们请他做的是 fine 的这个字，那 fine 这个字它是不是还有另外一个同义字是 this is a good book？ 好，那你要想哦，如果我们请他刻漏字的字是 fine 这个字的话，如果在你的 Wikipedia 的那个文本里面，你要记住，那个文本里面可能有好几百万个 article， 然后里面可能有好几千万、好几亿句不同的话。对不对？好，那你会发现，在刻漏字的情况之下，那些 training data 里面 fine 跟 good 在刻漏字的时候，他们常常可以互相 interchangeable。就说你会在文本里面看到 this is a good book， 也会看到 this is a fine book， 或者是不一定是 book， 或者说 fine art good art，fine house good house，fine 就是不管怎么样，你会发现。good 跟 fine 这个字在整个 train 的文本里面，他们常常相依出现，不是相依出现了，常常可以 interchangeable 了。好，那这个 neural network 就会知道说，这两个字如果它的上下文常常在 training data 里面是固定的，比如说 this is a book， 有时候是 fine book， 有时候是 good book， 那这个 weight 就会渐渐的会知道，它输出的时候可以输出 fine， 也可以输出 good。那既然它最后面这个 softmax 可以输出 fine 跟输出 weight 的 probability 都很高的话，那表示 fine 的它的 latent space 的位置跟 good 它 latent space 的位置应该都要很像，所以它后面那个 softmax 可以输出 fine 跟 weight 这两个的 probability 都会高。这是一个比较直观型的解释啊，希望你可以了解。所以借由这种 unsupervised learning 的状况之下，我们就输入大量的文本。只要文本里面 fine 跟 good 都是 interchangeable 的，他们的红色的那个 random space 就会很靠近，因为他们输出的那个 softmax 最后那个几率就会很靠近。那通常我们只是选几率高的那个嘛，可是在这情况 fine 跟 good 的几率可能都很高，只是可能有一个真的高一点点。所以至于说谁会高一点点，那就看文本里面谁这个在 book 前面出现次数比较多，的理应是这样子啦，然后它就可以输出这样子。所以这就是一个基本的文字转数字的 concept， 就是克漏字，可以吗？好，那我用英文再说一遍哈。So basically, this is the concept of how do you convert sequence data, especially text data, into numbers. Basically, you do a job. It is either supervised or unsupervised. It's sometimes called self-supervised. You collect all the sentences from Wikipedia or internet document. You put them into such kind of model. So that this model will learn good. For example, if your corpus, okay, there's always a sentence which contain fine book or good book, and then the weight, the green weight right here will learn such kind of things, right? So that after this weight, the softmax will output which word, which vocabulary in the dictionary would be the highest probability that can do such kind of closed task. Okay, let's take the fine and book for example. Okay, a fine book or fine good book, fine art, good art, fine house, good house, always I mean you observe such kind of training data frequently in your training corpus. Then this way will learn, okay, if I would like to close task and there is a book and in the middle there should be fine or close because it happens, it occurs frequently in our training data, and all those weights remember such kind of relationship. So at the end of this weight, okay, in the last layer, which I draw the red part, there should be a latent space. The latent space will specify will record all the information should be do such kind of output, and this weight will represent good or represent fine, so that the softmax will output will output the highest probability of fine or good as its result target y, which is the y right here, right? But after tons of learning in your corpus, okay, if fine and good are truly interchangeable, the latent space is the red layer, okay, the latent space right here, those values should be very, very similar for good and fine, right? Because all the information about the context, the previous word, the word next to your close word, okay, all the information should be in this red latent space. And if it is good, the latent space value of good and fine should be very, very similar in this latent space, so that the softmax can output high probability to good and fine. That is the basic concept of such kind of things. Basically, we do closed task, okay, because we don't have to label, because it is a self-learning. I mean, it is not a supervised learning or unsupervised learning. It's a semi-supervised learning. The answer is right there in your questions. Okay, so basic that is the concept. Okay, of course there are several different models for doing such kind of closed task. Okay, Hsiao. Okay, the word means W means word, T means the position. Okay, -2, -1. Okay, so we have a very short sentence, 5 words. Okay, but we like to predict what is the word in the middle. Okay, by using the word right here. Okay, that is Hsiao. For another model is called skipgram. Skipgram is that you input the word in the middle, and it will output 4 words, which can predict your context. t minus 2, t minus 1, t plus 1, t plus 2. Okay, because you have the corpus, right? Google download all the Wikipedia document, and they can split the sentence into such kind of 5 gram training data. Okay, you can do it in Hsiao way, or you can do it in speedgram. It's also it really doesn't matter. Okay, but the length and space right here, the length and space right here, it can represent the word. Okay, so that is Hsiao or speedgram. Okay, so the size right here, the size right here is 5, right? That's it's called a window size. You can, if you want to train your own Hsiao model or speedgram model, you can set this kind of window by yourself. Okay, so usually we use you can always find such kind of things right here, such kind of example right here. The quick brown fox jumps over the lazy dog. Okay, if your window is 5, so you have a sliding window, and you use this sliding window to create the training sample. Okay, for example, you want to do closed task, right? So you say, okay, for speak fox, okay, there's a neighbor words quick fox, there's a neighbor word brown fox, neighbor word jumps fox, neighbor words over. Okay, if it's at the head of the sentence, okay, we only have some symbols like this. Okay, so you can so basically, yeah, you just simply input those things. Okay, and so maybe it's right here. It's another example. As I mentioned before, if you want to input an vocabulary at the first place, okay, maybe you use 1 hot, right? Because we have to use 1 hot. So right here it has 10,000 words right here, and this word stands for ants. Okay, so it's a very sparse vector. So after that, we can do such kind of neuron things right here. Right? In here, you have 300 hidden neurons, or we say 300 different features right here. Okay, so that the input can do such kind of things, and we can, of course, at the end of your neural network, you can place a softmax there right here. So all the information should be okay. This example only draw 1 hidden layers, and of course you can have multiple hidden layers right here. Okay, but for simplicity, okay, we only use 1 layer, and it has 300 neurons. Okay, so this length and space. Okay, so we remove this one. Okay, supposedly we assume we have only 1 layer, and it's 300 neurons. Okay, but theoretically, when we do such kind of embedding things, there should be multiple layers, multiple neurons right here. Okay, and we only use the last layer as our length and space. But in this simplified example, okay, this is our length and space, because we have only 1 hidden layers. Okay, so basically it has 300 neurons right here. So basically it means the length and space has 300 dimensions. And for example, if we use the example right here, okay, if we input ants, and we collect a lot of different documents, and we like to do prediction. For example, prediction. So you can see that at the right hand side, its Y has also 10,000 neurons, the same as the input size, right? That is because that is the size of its vocabulary. So that is the probability of the first word, the second word, the third word to the 10,000 words, right? And all the information should be included in this length and space. So this length and space stands for this word ants. Okay, and of course, what is the weights right here, and what is the length and space, right? You calculate. You have to use tons of corpus, tons of documents to do such kind of training. So that simple 1 hot vector ants can be converted to a new namespace, and we use this 300 dimension namespace to represent this word ants. That is one of the way to do word embedding. Okay, and of course, as we mentioned in the previous hour, usually we don't have to manually do such kind of things. The only thing you have to do is to prepare the document you would like to use, and you feed them into Keras, and Keras will do these things automatically. So every time you input a word, you don't even have to create this one hot encoding table. Keras will do it by for you. The only thing you have to do is to input all the corpus, all the document data. Okay, they will try to do such kind of things. And every time you input a tag a word, it will give you the result in the namespace. That is the these 300 numbers is the representation of ants. And of course, since it is a closed task, okay, it still is a closed task, okay. Although this model is more simple, it only predicts the next word, right? There's the input word, that is the next word or the related word, okay. This namespace, in the namespace, okay, there should be another data which is near the ants, maybe some bugs, maybe some other insects, okay. In the namespace, all the insects will be clustered together in the namespace, okay. That is example, okay. So basically we can view it as this way, okay. It's a very simple example, exactly the same as the above figure, okay. So basically we will have one hot encoding. We specify what is the input vector, what the input word you want to know, and basically at the end of training we will get a matrix, okay. So it is specified, okay, this one would exactly the namespace value of this example. So basically, for example, if it is 1,000, we have 10,000 words, and the neuron is 300. So the weights right here would be 10,000 times 300, just like this one, just like this one. Okay, of course it is a simplified example. We have only 3 hidden neurons, right? And we have only 5 words to embed. Okay, so this matrix is very important. So basically, usually, if you train a model, and you have to, the best way is you preserve your weights, right? You preserve your weight. So basically, Google also provides such kind of information, so you can download. So basically, Google collect a lot of data, collect a lot of documents, and they do, no matter it's from skipgram or CBA or a neural network like this, this one, they will have such kind of weights stores saved. So you can simply just download those weights. So you don't have to train it by yourself. So most of the time, because it is a very intensive task, so basically we don't usually, we don't train it by ourselves. We use the training result made by somebody else, by Google, by Amazon, by Microsoft. They indeed put those weights in the internet. You can simply just download it and use the result. So you don't have to train it by yourself. Okay. So that is, so basically, yes, basically that you have a word vector like this, and you do softmax. That is the rest part. But and usually when we talk about vector, we use these vectors, these word vectors, to do some other things. Okay, that is how you do word embedding, right? Word embedding. And okay, I will skip this one. Okay. But how about I would like to encode a sequence? right? That is how you represent words by using metrics. And we have a very nice close task concept, right? This concept to help us to encode words into numeric vectors. So basically, if you want to encode sequence data, which is word data, okay, basically you can do this in this way, okay. You have a what we call language model, and of course it has several different inputs right here, right? Right, okay. And I would like to, and basically it is a sentence, and that is the word. And usually we call it token. And you can fit those words, those tokens, into a language model, which is a neural network. Usually it is a neural network. And this neural network, of course, it can be, for example, it can be the representation of the word can be multidimensional, so that it can be a vector or something like that. Okay, and usually, okay, we will create a neural network model. Okay, and there's a very specific things I would like to talk about is that usually when we do such kind of sentence embedding or sequence embedding, we have we usually assume we have some special tokens. In here, the special token called CLS, that stands for class, and that means the sentence starts. Okay, so the next token will be the first word in this sentence, and then so on and so forth. Okay, that's a specific token we'd like to use. So we will output, so that is output 1, output 2, output 3, output 4. So that is output this sentence. Okay, and again, if we would like to, sorry, I would have to move this one to somewhere. Okay, and if we would like to embed a sentence like this, okay, what is the concept we'd like to use? Again, we still use close. Okay, so how do we do that? Okay, I use the green. I use green color to represent this. Okay, so when you do training, okay, of course you have this kind of words, right? So when you do training, okay, you simply just, for example, we use this one. You simply just mask a random word in your sentence, right? So for example, in this example, that is book. Okay, so you have an output 04, which is quite related to the fourth input. Of course, this output still has some weights or some different structure. Of course, the square I write here, it should be a very complex neural network, not as simple as the C-ball. Okay, it's a very complex network, but we will skip it right here. Okay, however, there's a output 04, which is we'll take a look at all the other words used in this sentence, and especially output for this the fourth position of this word. Okay, and that means, okay, all the information about this sentence and this the fourth close word will be outputted right here. So basically it is also vectors right here. Okay, so usually, okay, I say usually we will do something like that. Usually we will do a classifier. So all four will be used as the classifier input. And then, again, the classifier will output vocabulary, which is a diction. Again, for example, that in this example, right, the first word is abandon, ability, right? So here, abandon, ability, something like that. And there is a vocabulary called book, and that is called Libra, okay, something like that. Okay, so basically, when we do such kind of sentence things, okay, we still use the concept of clause. Okay, we input the words and randomly do some mask, and at the output of the corresponding the mask word, there's a classifier which is also a neural network right here, and the output is the vocabulary, is the dictionary, and there's still of course there is a softmax right here. So if your training data is this is a book, and then here is the input, and I use a random a token to say, okay, that is the mask word, and you say, okay, after you have the neural network language model, and after you have the classifier, and then the output value of book should be 1 while you do the training. So you train the entire things, including the neural network right here, including the classifier right here, and it is still not supervised learning or unsupervised learning. It's still a self-supervised learning things, because you have the answers right here. So you have a question right here, input, you have the y, which is the answer right here. You can train the weights right here and write weights right here. That is the model, that is the classifier's weight. So gradually you input more and more sentence right here. You use the concept of clause, right? So basically, if your mask is, for example, I use another color, okay? If your mask is right here, and also you have to create a network right here, and here is a dictionary. We have several different softmax output right here. So basically, you can set a language model WM. It is a neural network, and for each output right here, it contains the result. It contains the information of the corresponding words and the words, its neighbor words, and the output should be a linear space, right? This linear space should be able to used and passed to a neural network to do the further classification. Okay, what is the highest probability that the highest possibility that this mask word should be? Okay, this whole concept comes from clause, right? So we will talk about then if those weights right here, they can do such kind of job, which I mean do clause job, and then usually this output, the output of CLS, which is this specific token, it also has several different weights, right? So it knows what is the sentence behind the CLS token. Okay, and so those weights are trained by closed task. And then right here, there's very important things. Usually we use the output of CLS, which is right here, the black one, as the embedding of this sentence. This is a book. Okay, did you get it? 01, 02, 03, 04, they are trained by using the data, the corpus. They know what exactly the position it is. They know what is the neighbor words. it use, and we have a closed task for them, right? So basically the weight will be trained by using the concept of closed, right? But there's still one output we do not use right here. It is the output of CLS. It also contains all the information about this sentence, and its position is at the first position, the CLS, right? So usually we use this output CLS as the sentence embedding, which represent all the information used in this language model. Okay, that's it. And of course, there are several different variations. There are several different neural networks. They try to do similar things, and they have different structures in this way. They have different closed tasks. But right here, I think that this concept is good enough for you to know the CLS is the we say the aggregate information about this sentence, and this sentence is this weight is trained by closed task. Okay, that is one of the tasks. Okay, and you might wonder, okay, is there any other concept that which is not closed? Yes, of course there is. Okay, so I will show you another one right here. That's called permutation task. Okay, again, we have a language model right here. Okay, and it is a very complex neural network. I will show you how complex it is, but I will not explain how it is. Okay, so we have a sentence, right? And we have different input. For example, this is a book. Okay, and as I mentioned before, this is a token CLS, right? And here's the O1, O2, O3, O4, O5, and that is the OCLS. Okay. Another task is like this. I collect a lot of different sentences from Wikipedia's document and put it right here. It has 5 different words and 1 star token right here. Okay, so basically the task I would like to do here is I don't want to input this is a book. I randomly permutation. I randomly do permutation. So for one of the training data, it could be book is this fine. That would be a training sample. I simply just permutate it randomly. Okay, the other training sample might be so you can use your training data to create a lot of training data, and each of them are permutation of the original task, original sentence. Okay, so what is the job we want to do is right here. After we input those training samples, okay, for each of the output, I still connected it to a small classifier, and this classifier will output our dictionary with probability. So there is a softmax, and the first word is abandon. Ability, and this is there should be one is book. So for this specific task, okay, I use the green one. I input this training sample, and my, that is x, right? And my y, I have a lot of y's, right? And for all 5, the classifier after it should be output book. It should output fine. It should put output is this. That is your permutation task. When you do training, you mutate, you permutate, you do permutation, right, as your input right here, and you tell the language model and its classifier how to output the correct order of the original sentence. So that is input and that is output, and you keep doing the things. And of course you can do fine book is this is as a training sample, and the output is still this is a fine book, something like that. So your weight will try to learn, okay, in the previous example, when we do close, the weights right here, they are trying to look at these neighbor words, okay? So okay, that this neighbor word in my experience, in my training data, it should output this. But in this task, this weight, they will try to, okay, I will try to do some permutation. Okay, so again, in this complex neural network, okay, all the information has been passed to different output. This output should know what neighbor words it used, and in this position, what kind of words should be output among these permutation words. Okay, so that is another task. So you can see that this part, the language part, okay, is the same as this part. So basically the weight is the same, but however we have different tasks. Okay, this task is used for permutation. This classifier is used for permutation. This class is used for close. So no matter what, this orange part, this orange language model, they indeed can comprehend the sentence you input, and they can summarize the sentence into a vector, and this vector can do permutation task, can do close task very well. So we believe those weights right here, they indeed know how English works, what is the grammar, what is the rules of, what is the context of English, this language. So that is the language model we use. Of course, there's tons of tasks, permutation tasks, there are insertion tasks, there are close tasks, but I think these two, I think that's good enough for you to understand what is the language model does. Okay, so basically, I think that is okay. So let's go back to our right here. So basically, that is the concept, right? So basically, what is the most advanced neural network which is used? Okay, we have two things right here. One is a transformer and BERT. So basically, a transformer is right here. So transformer is a structure. Okay, so that is the green the orange part I draw in the figure. Okay, it has a specific structure, neural network structure. Okay, it is it has several different layers, but it's very complex. It is not it is not our focus in our class, but it's a very basically you can simply, so we have to, the other is BERT, right? BERT is right here. So we Google still provide some example right here. So if you want to use transformer as your language model, okay, you can simply just copy the code right here. Okay, the other one is BERT. Okay, BERT is another model. Okay, but the concept is the same. If you want to use it, okay, so simply just copy this code right here. You can use the weight trained by Google. You don't have to train it, as mentioned before, you don't have to train it by yourself. Okay, you don't have to train it by yourself. So you can do some tests. After you have the transformer or a BERT model, words or sentence will become a vector. So after you have those vectors, you can do a lot of different job. For example, if you want to classify, so here is the here's one of the example I would like to show you before. Okay, right here. If you have a BERT model, if you have a transformation model, or if you simply just use virtual vector model, which is okay. Okay, and we can see that there are 14 different tactics, but they describe different stages or different phases when attack comes into your when attack try to attack your system, right? You can see that there are several different descriptions right here, and they are related to reconnaissance. There are several different description. They describe the techniques used under reconnaissance. Okay, you can even just click. Well, there are even more text right here. There are even more descriptions or some other documents right here. They all talk about the concept of reconnaissance, right? And of course, there are some other, for example, initial access. Okay, again, several descriptions right here, right here, right here, and you can simply just click the specific technique, and it will describe what is the technique talk about. So basically, we can do a very interesting things. Okay, so right here, so let's go back to our basically, you can use a language model right here. Let's say it is a BERT. So BERT is a very complex neural network structures, but all the weights has been trained by Google, and then put it some I think we can go back again. Okay, okay, and you can simply just BERT weights. Okay, and you can find a BERT the GitHub of BERT. Okay, you can see that there are several different versions of BERT. Okay, H stands for hidden neurons, right? With small BERT has a small neurons, large BERT has a larger number of BERTs, which is right here. Okay, so you can simply just download. It's right here. Okay, BERT large, BERT large, BERT large, and BERT. I think that there is a BERT base and BERT here. BERT tiny, BERT mini, BERT small, BERT medium, BERT base, BERT large, something like that. There are several different parameters used to construct the language model they use. Okay, the larger one, which is more complex one. Okay, but those weights are available. You can download those weights from this GitHub. Okay, so let's go back to here. Okay, so you can simply download a BERT model from GitHub, from Google's GitHub. Okay, so it tells you, okay, you can input CLS right here, and your token right here, so on and so forth. So basically, what you can do to analyze the attack, okay, you can get all the document on the MITRE attack, as you see before. Okay, there's a document, right, and there's a reconnaissance. There are a lot of different sentences in the reconnaissance document, right? So you can input those sentences into a language model, and which is BERT, and you download the weight from BERT. Okay, and then you can say that, okay, I have a lot of outputs right here, and of course there's an important output. That means, all the information right here, those tokens, will goes to here. So it is a vector represent all the necessary information for this language. Okay, English this language. Okay. So after that, I can design a very simple classifier, and it has 14 output. The first one is reconnaissance. The second one is initial access, so on and so forth, execution, so on and so forth, and the last one is impact. So basically, you can learn. You can try to learn what Google did, right? So basically, the model is from Google. You simply just download this weight, but you can create a classifier by your own after this OCLS, upload CLS. So when you collect the data, the document from MITRE ATT&CK's website, okay, you can put a sentence right here, and all the information about this sentence will be right here, OCLS, and you use this OCLS as the input in your own classifier, and says, okay, I would like to, it is 1000, because this sentence is from reconnaissance. You can collect all the sentence from reconnaissance, initial access, impact, execution from the entire website, and you know the answer because you know which page the sentence belongs to, right? So you know what is the tactic used, right? So after that, you can get this weight, and of course, you will slightly change this weight. This job, this job is called fine tune. That means the weight you obtain from the Google is W, black W, but you can attach your classifier after OCLS and then continue to do fine-tune job. And this job was specifically for identifying this sentence, this input sentence belongs to which tactic. Okay, after that, your weight right here will be slightly fine-tuned, and your weight right here will be tuned. And after this training job finished, and then you can do something like, okay, I can randomly select one of the sentence from the internet, and it is related to some security actions, and you input this testing example into your language model. So it's right here to here and to here, and it will tell you what category this testing sentence belongs to which MITRE ATT&CK tactic, right? So basically, language model is the model that you can convert your sentence into vector space, right? Into vector. But after that vector, okay, you can design your own. We call it the downstream application. You can design your own downstream application, which is the red part, to do whatever job you like to do. Most of them are classifier, I believe. Okay, so you can train your model based on Google's weight, and you can fine-tune those weights and your classifier weights by using the document you use. For example, I use right here is the web pages from MITRE ATT&CK, and their label is their tactic. So that every time I find a sentence in a security report, I can feed this sentence into the model I create right here, so that it can tell me this word described which kind of tactic defined by MITRE. Okay, of course there are several other applications can be used by such kind of this kind of structure. Okay, maybe you need a language model like this. Okay, I would like to create a language model right here. So we have a lot of tokens right here. So maybe you can concate a neural network classifier right here. What is that? It is for news categories. So every time you find the news, right? And there are a lot of sentences right here. You simply just input those sentences in this language model, which is provided by Google. And you can use the category right here to make sure, okay, that is a political, that is a sports, that's entertainment, that is a lot of different jobs you can do right here. That is the downstream application. You can design whatever downstream application you like, and you can deal with articles, sentence right here. So you can train your model and fine-tune your weight by using old news. But every time that when the new news comes in, you can pass the news sentence into this model and into your classifier. In your classifier, will base on the old knowledges and give you, okay, that is a political news. So you can automatically put these new articles, this new news under the political section. You don't have to manually design such kind of things. You don't have to manually specify which category this news belongs to, right? You have such kind of things. So I think that is what I'm going to. So I think that's all what I want to share with you in this class. So if you're interested in language model, okay, I only give you some basic introduction to language model. So if you're interested in it, you can take a look at this reference. You can take a look at this code and this code right here. Okay, Google provide how do you write code using TensorFlow or Keras to implement the concept which I show you in my figure. Okay, so this class that's all what I want to share with you. So I will announce the final exam this afternoon, probably at 3 p.m. So after you just refresh this website. Okay, I will announce this right here and also right here, also in the announcement sections. So basically you have 1 week to finish all things. Good luck. Okay, I think that's all. Okay, bye-bye. If you have any question about your score, your final project score, I will announce it before we submit it to the university. So you will get your score before we submit it to the university. So if you have any questions, you have any problem, you have any question you want to ask, you can send email to TA or me. We'll try to explain it before we send it to the university. Okay? Okay, that's it. Thank you. Goodbye.